Okay, Ed, thank you very much. So, all of you know that SABRE frequently operates in a limit which is very non-intuitive to people who do NMR, where scalar couplings, resonance frequency differences, exchange lifetimes are all comparable to one another. And as a result, one's intuition has commonly failed, at least for us. And I'm going to talk about a case where, to me, also this turned out to be something very highly non-intuitive. And I think it has consequences for a lot of different SABRE experiments. What I'm going to show you is that in many common reagents, ones which have heteronuclei as well as protons, there's an efficient pathway to creating two-spin order in the ligand, which is essentially field independent and has potential implications for a lot of different experiments. So let me go on from there. So I'm not going to go through and explain SABRE to you, except to remind you that there are essentially two different regimes that most low-field SABRE operate in. One is roughly 6.5 millitesla, where the chemical shift difference between the protons on the ligand and the protons in the hydride is comparable to the coupling between the two hydride protons. And also the regime for heteronuclei, which is typically a small fraction of a millitesla, or microtesla. Sorry, that's micro, not milli. And in that regime, it's the resonance frequency difference between nitrogen-15 or proton or carbon and proton, which is in that limit. So, in fact, the dynamics are actually pretty complex, and those are justified by saying that this is the limit where you make those couplings similar. Originally, there was a lot of discussion about level anti-crossings as a way to analyze this. Level anti-crossings do work, but only in the limit where JHH dominates everything. In something like SABRE sheath with nitrogen-15, they can easily be something like an order of magnitude off, and we wrote a paper a few years ago talking about all of this. But the bottom line is that high-quality simulations do a very good job of replicating what you see in experiments. And so this is a SABRE sheath experiment in nitrogen-15. You're measuring the Z magnetization by giving a 90-degree pulse and looking at the transverse magnetization. And as you can see, simulation experiment lines up pretty well. You get a nice resonance at a small fraction of a microtesla, and outside of that regime, you see essentially nothing. Now, an easier way to understand this, which I'm going to go through because it is actually useful for what I'm going to do next, is to look at the order which magnetization is actually created. So you start with singlet order in the density matrix, I1.I2, and just use the von Neumann equation and find what terms first give you a magnetization. And that paper that I just showed you goes through this. There are 8 different pathways. I've shown a couple of them here. You go through initial IZ1, IZ2 order, for example. You create 3-spin order with one coupling. You get rid of the coupling to the hydride proton, which isn't coupled to the nucleus you're interested in. And then the chemical shift difference in SABRE, or the resonance frequency difference in SABRE sheath, allows you to change the phase here, and then one more coupling turns it into an observable operator. So the critical point is that chemical shift difference, which is what creates a resonance. It creates a resonance frequency difference between L and H, or the gyromagnetic ratio of L happens to be nitrogen-15. Okay, so all this has been well understood for a while, and we thought we had a pretty good understanding of how SABRE actually operates. And so, for example, here is SABRE roughly at the maximum for nitrogen-15. This is showing the FIDs as I reverse the magnetic field, and you see, as you would expect, in-phase peaks that reverse by doing that. But if I go a factor of 100 away from the resonance frequency, the FID has hardly decayed very much at all, except that it starts at 0. And even more intriguingly, if I give a negative magnetic field versus a positive magnetic field, instead of it inverting, it stays exactly the same with this antiphase magnetization. In fact, experimentally, we can vary this field over about a factor of 100 in the laboratory, including the Earth's magnetic field sitting in the laboratory. So you can do just fine setting the SABRE apparatus bubbling just with no shield, no magnet, and produce magnetization, which transfers easily into this antiphase magnetization. When you flip the field, it makes no difference. And it produces comparable proton and nitrogen signals. That is, if I give a proton pulse, I see a serious proton FID. If I give a nitrogen pulse, I see a serious nitrogen FID. But these frequencies here are very far away from the frequencies of resonance that you'd have either for SABRE or for X-SABRE or SABRE sheath. Okay, so what's going on here? What's going on here is you're actually directly producing two-spin order on the ligand target. And in the questions, if somebody wants to know the differences in the Zulf limit, I can go through and do it. But here I'm really going to be focusing on the limit that is off resonance, or more specifically, the limit between the SABRE resonance and the X-SABRE resonance. Okay, so to do that, I'm going to set up a model similar to what you heard a couple of talks about, where I'm going to take two nuclei actually sitting in the ligand, in this case, a nitrogen-15 and a proton. Now, of course, I can put the other protons in, but this is going to be enough to explain what's actually going on here. And I'm going to start by just talking about the regime between SABRE and SABRE sheath. So 10 to roughly 1,000 microtesla, where neither one of those mechanisms is very efficient. But in that limit, we can ignore the resonance frequency difference between the protons, although we do have to keep the resonance frequency difference between the nitrogen and the hydrogen. Okay, so we've got a bunch of couplings sitting here. And in fact, this is what the Hamiltonian looks like in the rotating frame when you do that. So you have the off-diagonal term here that's sitting between the ligands and the hydrogen. But from there, you have actually a very efficient fourth derivative term, which takes you straight from Z magnetization in the singlet through 3-spin, 2-spin, 3-spin, 2-spin, or 3-spin, 4-spin, and so forth. So this is of exactly the same mathematical order as the SABRE that I did for you before, but you'll notice something very different here. There is no resonance frequency difference contained anyplace in this. When you go through all of the possible terms, you find that the first term and the last term always has to be the SABRE coupling, in this case, the coupling between the hydrogen there and the hydrogen there. And this coupling, of course, matters, but the difference in the couplings between this and this and this and this now comes into the problem. And the mathematical reason for that is very simple. If I have this nitrogen-15 as a spin up, it shifts up this resonance by that J coupling, and it shifts up that resonance by that J coupling. And if those two things are different, it creates a resonance frequency difference exactly the same way as a magnetic field would, except it's independent of the magnetic field. Okay. So this explains actually all of the observations. It's fully field size and direction independent within those limits. LZ-SZ happily accumulates in the ligand itself, even at low field. It creates hydrogen and nitrogen magnetization at the same time, antiphase magnetization. However, for example, in an AX spin system, 100% of antiphase magnetization converts into in-phase by just waiting a delay. And so I'll model pyridine in this case with 2 orthoprotons. And the transfer of the antiphase magnetization that's created here is about 50% efficient at T equals 1/4 J. But that's enough for us to actually infer from experiments the efficiency of creating this spin order. And what you can see is the efficiency of creating the 2-spin order in the ligand off resonance is very nearly the same as the efficiency of creating the 1-spin order on resonance. Okay. So this has a variety of implications for many different SABRE experiments. Every optimization that I have ever done, and that I think anyone else has ever done, has been trying to optimize the magnetization as in LZ. after the pulse sequence, after the SABRE exposure is done. But in fact, what you really care about is what we'd call the effective magnetization. In other words, what would be the largest point in the free induction decay once you transferred it to high field? Because if you gave another 90-degree pulse, you could turn that back into Z magnetization. And that's a different strategy and likely implies different efficiencies. It also implies a variety of different and possibly much more efficient strategies for high field SABRE, because this mechanism works very well at any field strength if it isn't truncated simply by the resonance frequency differences. And in fields, for example, hundreds of millitesla, a regime that's quite interesting for imaging, this could be done very well with just a rare pulse sequence to take care of the difference between the proton frequencies while keeping the differences between the proton and the nitrogen frequencies. I'm not going to have time to go into it here, but as opposed to most of the high field strategies, which really depend on singlet and are poisoned by alpha beta minus beta alpha, this works just as well, in fact, in some cases better, with a 50-50 mixture of alpha beta plus beta alpha and alpha beta minus beta alpha. It also predicts a variety of new SABRE resonances. It turns out that you cannot directly polarize a carbon-13 methyl group by SABRE. And the reason you can't do that is because of this coupling, which means that in the 6.5 millitesla regime, the hydrogens are 130 hertz away from resonance. And so in order to make SABRE work for direct polarization of that, you'd need to go up to about 120 millitesla. And in fact, it's going to be pretty strongly dependent on the chemical shift difference. So there's a variety of new mechanisms that this actually proposes, which are going to be intriguing to explore. Okay, so I hope I've kept this relatively short because I'm guessing there could be some questions. My favorite quote in science is this one from Arthur Schopenhauer. It's sometimes attributed to Schrodinger, but I think this is the right source. And in fact, many people have seen anti-phase order when they've gone through and done SABRE experiments. But the realization that this is something that is direct generation of spin order and that it is largely field independent has at least not been noted by us. And I think it leads to a bunch of other pathways which are intriguing. And now, one reason why this often is not noticed is if you do a hyperpolarization experiment and you have the bubbling apparatus sitting in, you probably have lousy homogeneity when you transfer it into the high field. And with that lousy homogeneity, if the coupling is small, it will go away due to inhomogeneous broadening before you see it. But there's plenty of ways to compensate for that. But that just might be the reason why people haven't discussed this so much to now. So with that, I will thank Luke, Jake, Shannon, and NSF, who actually funded me last year in one of the worst years in history. If any of my grant reviewers are on this talk, thank you very much. Okay. And with that, I'll terminate and ask for any questions. Thanks.
Really exciting and intriguing talk. The floor is now open to questions.
Hi, Warren. Do you think that this effect or this approach to explaining the antiphase behavior that you see in SABRE are heteronuclear cases like in 10, like what Simon Duckett reported in 119 and then we've seen in 117? This might explain how to think about the antiphase 10 signals that we see, particularly since that the optimal field is usually in this intermediate regime between what's ideal for proton and what's ideal for a SABRE sheath.
And it certainly does, because this is a completely non-resonant effect. And so but it simultaneously produces both the proton and the X polarization. And I think there's a lot very interesting still to explore. Now, in the limit where you go to extremely low fields, you start doing things like pumping heteronuclear singlets as well, because there's a direct magnetization for transfer from the hydrogen into a direct heteronuclear singlet, which, of course, the way we do the experiment, shifting it back to 1 Tesla just goes away quickly. But yes, there's a bunch of things that we have not had time to look at yet that I think are intriguing applications of this.
Malcolm Levin.
Yeah, thanks, Warren, and very, very interesting. I guess, yeah, it makes complete sense, doesn't it, that you would generate all sorts of different forms of spin order in SABRE, and well, rather than being fixated on the magnetization, then yes, it makes sense. So I know there has been work by maybe yourself, but others, I believe, also on generating, for example, long-lived states or singlet order on the ligand with 2 carbon 13s, that sort of thing. How closely related is this to that, or is it an entirely different thing, or is it just another sort of branch of the same type of phenomenon?
Well, so for the heteronuclear singlet, yes, indeed, we have, or the homonuclear singlets, we in fact, of course, have done this. And what I would argue is I showed you in the simulations that our experiment differs from the simulation at very, very low field. That's just because making singlets is actually very efficient. There's a nice 4-step trip to make a singlet, starting from singlet hydrogens in the hydride. So this relates to that, but I would say that we never thought about the idea that the heteronuclear ZZ order is, of course, quite stable and can accumulate very happily, both at low field and can then be transferred into real antiphase magnetization. So there is a relationship.
Okay, thank you.
Thank you. Very interesting as usual. Maybe I missed where did the 120 millitesla come from? And also related to that, I think there's already publications by Alexei Kirutin, Novosibirsk group, showing extremely strong carbon empty phase signals at around 90 millitesla. But where did 120 come?
So the 120, that's going to be dependent on the resonance frequency difference between the hydride protons and the target protons. So if you take 25 ppm as an example, but of course that varies depending on the species. If you ask for 25 ppm, where do you get a resonance frequency difference of 130 hertz, which would cancel out the J coupling? That's what happens. But the interesting thing about that is what that means is that for proton spin up, you hit exact resonance when you do that. And so you go slightly off into a standard SABRE effect. For proton spin down, you're 270 hertz away from resonance. And so what you're actually making is an equal amount of IZ and IZSC. So half of your spins polarize, the other half do not. That's 1/2 plus IZ times SC. And in fact, it is going to be strongly dependent on the chemical shift difference between the species. So it also gives you an opportunity of getting some chemical selectivity, which is not normally present at 6.5 millitesla.
Really exciting. Let's thank Professor Warren one more time.